Right, so we're going to think now. This is an exothermic reaction. Hydrogen plus chlorine giving me 2 HCl. Delta H for that is negative. It's an exothermic reaction. Why is that an exothermic reaction? Well, we're going to look at doing some calculations that we can show that that's an exothermic reaction. But I want to just talk you through the process of what's actually happening. Down here, so I'm going to draw, I start with 2 hydrogens combined together. They are reacting with 2 chlorines combined together, like so, to give me 2 HCl, like so. So, the first thing, at the moment, these guys, they're alright, they're quite happy, they're bonded together, these guys are okay, they're bonded together. Before I can get them to react, I have to split them up. So I have to, as a chemist, come along and I have to break these bonds. So I come along and I break that bond and I break that bond, and that would produce little hydrogen atoms, so 2 hydrogen atoms and 2 chlorine atoms, and then these guys recombine, so they come along and they form new chemical bonds. So hydrogen and chlorine get together like so, here and here, so they are forming chemical bonds. So the first step in any chemical reaction is to break the bonds, and then the second step is to make the bonds. Breaking bonds is an endothermic process. I've got to put energy in to break bonds. So breaking bonds is endothermic. That requires energy. Making bonds is exothermic. You get energy back from that. And it's the balance between these 2 figures as to whether overall it's an endo or exothermic reaction. Now, what we'll do is we'll plot this on our little reaction. So, down here, I start with, so I'll draw them out, 2 little H's joined together and 2 chlorine atoms joined together, like so. I've got to put energy in to break those guys up. So, is it going to get higher? Are the atoms going to be higher or lower? If I put energy in, going to be higher. It's endothermic. So, up here, on this level, are 2 hydrogen atoms and 2 chlorine atoms, like so. So I'll do a little arrow. That is breaking bonds, which is exothermic. Sorry, endothermic. Oh, that was a massive fail. Okay, now these guys are going to join together down here. They're going to make some bonds. That is exothermic down there. So this is making bonds, which is exothermic. I get energy back from that. Remember, that's a negative figure. It goes down until I get to this, which is 2 hydrogen chloride molecules joined together, like so. And then finally, what is that figure from there to there? The difference. That is delta H, which is negative, it's gone down. So when we talked about rates, we talked about something called activation energy, which is the minimum energy required for a reaction to take place. This distance here to here is the activation energy. If I can't break these bonds, if I can't give them enough energy to get here, I can't get these. Before I do anything, both these bonds have to break. So that is called the activation energy, that there. So what I'll do is I will plot that in a way that you'll expect to see it in the book. So if I go back, my reactants are H2 and Cl2. It was a exothermic direction, so I made 2 HCl and we said delta H was negative. That's what we were doing at the start of the lesson. Yep. Are we happy with that? So all we've done today is done this little hump. When I'm breaking the bonds, ooh, and then I go wee, like that. And then this distance from here to there is called the activation energy. So at the top of this hump, that's where my atoms don't have any bonds at all. No bonds, they're all on their own. Ah. So I've broken all the bonds, that's endothermic, I'm getting higher, 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 higher. I've broken all the bonds, then they remake them and they come all the way down to that. Notice no arrows on this hump at all, don't put arrows on here, just keep like that. So the way you have is you should have an arrow going up like so, and an arrow going down like so. So no arrows on this curvy line, an arrow going down and an arrow going up. The red arrow is my activation energy and the black arrow is my energy change for the reaction. So what we do is I'll do a similar one but do it for an endothermic. So for an endothermic reaction, if my reactants are here, you just do the same as we were doing. My products are higher. This distance from here to here is delta H, which is positive. And my activation energy goes from here to there. But now the activation energy is that. So the red arrow is my activation energy. So it's exactly the same thing, but this line just gets shifted up. So before, this line was down, so this carried on, and that went down. Now this one's higher. So the way I'd always do this is draw the bit in black first, and then do the red line, because all the red line does is connect these two together. And then the red line has to start from where your reactants are, all the way to the top of the hill. So you think my reactants, they've got to go, if you think of them as they've got to go, oh, get all the energy, whee, free atoms, and then they make bonds like that. So this process is endothermic, and this process is exothermic, because it's coming down. Diagram. So if we go back to this, this is showing an exothermic reaction. That's delta H, so that's the energy change that you observe. That's my activation energy. We need to just think about how a catalyst works. When we looked at rates, we said that a catalyst lowers the activation energy. So you can show that really easily on one of these diagrams. If they ask you, just do another little hump, which is in blue. It just is slightly lower, and then that distance there in blue is my activation energy with a catalyst. So it just shows how it lowers the activation energy. So rather than having to get all the way up here, they only need to get up here. Has it changed delta H at all? Has it changed? It hasn't changed the energy that I observe. It only changes the hump that they've got to get over. So it just makes it easier for them to get over that hump. And equally for this one, for an endothermic reaction, you do exactly the same. You would just do follow the same pattern as the red line, but just lower, and then that there is your activation energy with a catalyst. Like so. So if they ask you to do it on one of these diagrams, you just do a lower hump. You just got to make sure it's lower than the red hump. Things like that.